Let's look at section 9.2. We're going to look at three-dimensional coordinates and go into vectors in 3 dimensions. So here's how we draw our three-dimensional coordinate system. The paper itself will be the YZ plane. We'll have the y-axis going from left to right, where the positive y-axis is drawn solid here. The z-axis goes up and down, and the x-axis is coming out of the page. It takes three-dimensional space. Maybe a model of three-dimensional space will be the room that you're sitting in. And if you look at the corner of the room, the edge that goes up and down will be the z-axis. And the edge that goes from right to left will be the y-axis. And then the edge coming toward you will be the x-axis. It takes three-dimensional space and cuts it into what are 8 octants, where the first octant is where x, y, and z are all positive. And I'm really not sure how they're counted from there, but I know that they're 8 congruent clunks of space. The xy plane, I'll shade here in red, will be drawn here. There's the xy plane. That's where z is equal to 0. The xz plane, I'll shade in blue. That'll be where y is equal to 0. So if I extend that down infinitely in each direction, and down is the yz plane, and that's where the xz plane, where y is 0. And then in the yz plane, I guess I'm out of colors here, is where x is 0. The yz plane, I'll kind of guess do in black, in a thicker black. Oh, that's a thicker blue. So there's the yz plane right there. So the yz plane is there. The xz plane comes out here. I'm sorry, the xy plane. Good gosh, I can't get anything right here. It's the xy plane out here. And then the yz plane is with y is equal to 0, the xz plane. I just drew the xz plane. That's the xy plane. Okay, good gosh, drawing all over the place. Let's get that off of here. Let's get all that off. I don't want any of that on. You can't see it then. Okay, well, there's our coordinate planes. Got too thick of a line going here. Okay, let's show you how to plot some points. I've drawn the xy plane as a parallelogram with the z-axis coming up. So if I wanted to plot the point 2, 3, 5, then I go out 2 units in the x direction, and then 3 units in the y direction, and then down 5 units in the z direction. So now I'm going underneath this. So here's the point P. Point Q, I go back 1 in the x direction, to the right 2 in the y direction, and then up 4. So here's the point Q. And then R, I go out 1 in the x direction, back 2 in the y direction, and then up 3 in the z direction. So I'm going for point P, I went over, I think I went over 2, across 3, and then down 4. There's point P. And point Q, I went back 1, to the right 2, and then up 4. We can find the distance between points by using the same distance formula that we had in 2 dimensions and just extend it to 3 dimensions. It's the Pythagorean Theorem, where the distance is going to be the square root of the distances between each coordinate squared. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, all under the square root sign. So distance is going to be positive. So let's look at our example. Let's find the distance between point 2, 3, negative 5, and q, negative 1, 2, 4. So let's see. I'll plot them again. So here's the z-axis, the y-axis, and then the x-axis coming out. So 2, 3, negative 5. So 2, 3, negative 5. And negative 1, 2, 4. So we're looking for this distance right here. I'm going to have to make that point a little bit bigger. So according to the distance formula, I'm going to take the square root. The order in which I subtract doesn't matter. But let's go with negative 1 minus 2 squared. Plus, right, it comes from the Pythagorean Theorem, so in between we're going to have plus signs. Now I have 2 minus 3 squared plus 4 minus a negative 5 squared. So I've got a negative 3 squared is 9, negative 1 squared is 1, 4 plus 5 is 1, 1 squared is 1. So the distance between those is the square root of 11. Distance is a positive number. If we look at some graphs in 3 dimensions, planes will be things which were linear in their equations. First degree equations in 1, 2, or 3 variables are all graphs of planes. For instance, the plane z is equal to 4. If I draw my 3 space here, the plane z is equal to 4 will be parallel to the xy plane through z is equal to 4. I'll just draw it in the first octant, and you use your imagination that this is going back into the paper parallel to the xy plane. The line x plus y is equal to 2, line in 2 dimensions becomes a plane in 3 dimensions. Let me draw that over here. There's x, y, and z. X plus y is equal to 2 would be a line that has an x-intercept of 2 and a y-intercept of 2. So there's the trace of that plane. In the xy plane. Now make that a plane parallel to the z-axis, so I'm just going to kind of draw again the first octant of that. We typically represent planes by parallelograms, and then just to imagine that that is going infinitely in each direction. Then to get a graph of the plane 2x plus 3y plus z is equal to 6, well, we'll put that right here. The intercepts of that, 2x is equal to 6 when x is 3, 3y is 6 when y is 2, and z is 6 here. So the trace would look like this triangle here. Now, to make that a plane, just imagine the 3 sides extending infinitely in each direction. So first degree equations are planes. Any other graph in 2 dimensions becomes what's called a cylinder in 3, where the cylinder doesn't have to be closed. For instance, the cylinder y is equal to x squared is a parabola. Right? Y is equal to x squared is a parabola that opens up about the y-axis. So y is equal to x squared in the xy plane does something like this. And now make that into a cylinder like that. X squared plus y squared is equal to 4 is a circle in the xy plane of radius 2. And so if I draw that circle, and then of course it goes back, and then make a cylinder opening up about the z-axis. So if I had, for instance, x squared plus z squared is equal to 4, that cylinder would be symmetric to the y-axis, opening left and right. Z squared plus y squared is equal to 4 is a cylinder that comes out symmetric to the x-axis, coming out front and back. Any graph in 2 dimensions becomes a cylinder in 3. Spheres will be the set of all points equidistant from a fixed point. So if I take my distance formula and set it equal to some distance r and then square both sides, we'll have the equation x minus a squared plus y minus b squared plus z minus c squared is r squared. So that's going to be a sphere whose center is a, b, and c, and whose radius is r. So the first one I've written is a sphere whose center is at the origin and whose radius is equal to 2. So if we can get the equation in the standard form here, then we can find out where its center is and what its radius is. So I've given you an example of one that's multiplied all out. We're going to complete the square to put it in that standard form. So let's do that. Let's group all the x terms together. So let's move the 6x over, and we're going to leave a gap right here. Then let's take the y squared, move the 4y over, leave a gap there. Then we've got the z squared, no other z terms, so the z hasn't been shifted up or down the z-axis. And now let's move that 3 to the other side. So we're going to complete the square, if you remember how to do that. We're going to look for a number that we add inside here so that x squared plus 6x plus that number factors as a perfect square. But if I'm adding that number here, I have to add it over here as well. We're going to add another number in here. If I add a number there, I've got to add it over here as well. Remember how we pick that number? We take 1/2, the middle number, squared, and it goes here. 1/2 of 6 is 3, 3 squared is 9. Do it again, we don't have to worry about the sign because we're squaring. 1/2 of 4 is 2, 2 squared is 4. Now, x squared plus 6x plus 9 factors as x plus 3 all squared. We always take the sign of the middle term. 3 squared is 9, 3 plus 3 is 6. Then the middle sign here is a minus, so we're going to have y minus 2 all squared, because 2 times 2 is 4, and 2 plus 2 is 4. In fact, negative 2 plus negative 2 is the negative 4. Then on the right side, we add those numbers together, and I have 3 plus 9 plus 4, so that's 13 plus 3 is 16. And this tells us that our center, remember the center is things shift backwards than what you think, so this minus a here shifts to the right a units, x plus 3 shifts to the left 3 units. So the x is left 3, y is right 2. Oops, I lost my z squared, there it is, plus z squared, and there's no shift in the z direction. So it's a center at negative 3, 2, 0, and radius of 16. Let's see if we can draw that. May have bit off more than I can chew. I don't know that I can draw this. Let's see, -3 is back here. 1, 2, 3, 2, and 0. So there's the center, and now we go out 4 units. So let's see, I went 3 units. 3 units gets me back here. That's 4 units. And so 4 units, 4 units. We've got some sort of, oh baby, that's good. There's our sphere. Yeah, pretend it looks like a sphere. A sphere or a blob. But its radius is 4. Okay. Now we talked about vectors in R2 as having an initial point and a terminal point. Or if we write them like this, then that's a vector in standard position. If I go back to my 3-dimensional space and I go over A units here and B units here and C units there, over, up, then I've got that vector in standard position. Probably should make it in another color. We can find a vector the same way we did using coordinates in 2 dimensions. We can use our difference between the terminal point would be Q, and the initial point P. So my x coordinate or x component would be 4 minus 1, and then 0 minus 2 would be the y component, and 5 minus 3 would be the z component. So I can write that as 3, -2, 2. The unit basis vectors are vectors whose initial point is the origin and the terminal point is 1 unit away. So here is the unit vector we're calling I. Here's the one we're calling J. And then here's the one that we're calling K. We can write every vector as a linear combination of the unit vectors. For instance, above, the vector whose x component is 3, y component is -2, and z component is 2 can be written as 3i, because 3 times 1, 0, 0 gives me the 3, plus, well, I guess I should use minus, so let's do minus 2j plus 2k. So I'll try to put the little hats over the I, j, and k so that you know they're not variables, that they're representing the unit basis vectors. So we have 2 different ways that we can write vectors, with the sharp brackets or with the I, j, and k notation. I'll try to put the vector symbol above it if I'm using a variable. Your book will use boldface print to denote a vector. So we can write a vector either with the cute sharp brackets or with the I, j, k notation. Get used to doing both. A lot of times in physics we'll use the I, j, k notation. In Cal 3 we mix them up. We do a little bit of both. We can find the magnitude of a vector in 3 dimensions the same way we can find the magnitude of a vector in 2 dimensions. It's the distance formula, really. It's the square root of the sum of the squares of the components. Okay, so for instance, if I use my vector PQ above, let's find the magnitude of vector PQ that we had in the last example. So I'm finding the magnitude of the vector 3, -2, 2. So I square each component, 9 plus 4 plus 4, and then I take the square root of that. So 9 plus 8 is 17. It's a vector whose length is the square root of 17. In the next example, we want to find a unit vector that has the same direction as PQ. In the last section, in 2 dimensions, we found that a unit vector in the same direction as a given vector is just a scalar multiple of that given vector, and that scalar is 1 over the magnitude of that vector. So in other words, we scale it down to a length of 1 to get the unit vector. So we're going to do it here. We've got a couple of steps first. We've got to find our vector PQ. So we subtract components. I'll use this notation here. 0 minus a negative 1. The order is important. 7 minus 5. We always do terminal point minus initial point. So negative 3 minus 2. And we get the vector 1, 2, negative 5. Or if you like the IJK notation, it's 1i plus 2j minus 5k. And we wouldn't write the 1. That would be redundant. Now to get the unit vector in the same direction, we do scalar multiplication. We take that vector and we find its magnitude, and we're going to put it down here. 1 squared plus 2 squared, whoops, I kind of got carried away with that 2, plus 2 squared plus negative 5 squared, and then we multiply that with 1, 2, negative 5. So let's see, 25 plus 4 is 29, I get 30, times 1, 2, negative 5. You can leave it out there, you can put it inside. Remember, scalar multiplication is on every component. Or you can do the IJK notation. Again, the operations of addition and subtraction, scalar multiplication, are just the way you would want them to work. So here in this next example, we're going to subtract 2 vectors, v minus w, so you subtract component-wise, and you get a vector. So I take my I component, subtract my I component, 2 minus 5 gives me negative 3i, minus j, there's a missing j over here, so its component is 0, so that stays at minus j, and then 1k minus 6k gives me minus 5k. There's subtraction. Here we're doing addition and scalar multiplication. So let's start with 3v. Take vector v and triple each component. And so 3v would look like 6i minus 3j plus 3k. Now I'm adding that to 2w, so that'll give me 10i minus 12k. Now add component-wise, 6i plus 10i is 16i, minus 3j, 3k minus 12k is minus 9k. Easy enough? There's the addition, subtraction, scalar multiplication, same as in 2 dimensions. I probably didn't mention this in the last section, but 2 vectors are parallel if one is a scalar multiple of the other. In this example, the vector 4, negative 6, 10 is parallel to 2, negative 3, 5, because I can take this vector, multiply it by a half, to get that vector. They have the same direction, but different length. And if that occurs, then the 2 vectors are said to be parallel. And that's it. That's all I've got for section 9.2. It's pretty much the same as section 9.1, except I've got the added bit in there about what it looks like to do some point plotting and graphing in 3 dimensions.